Good morning, everyone. I am Vinitha, Associate Professor in the Department of Electrical and Electronics Engineering, RMD Engineering College. Today, I am going to explain how to draw impedance and reactance diagram in power system analysis. So, before going into the topic, let us see the single line diagram. We all know that the power system, which consists of various components like alternator, power transformer, transmission lines, substation transformer, distribution transformer, loads, etc. And all these components are easily represented by a diagram which is called as single line diagram. A single line diagram is a diagrammatic representation of power system in which all the components are represented by their symbols and the interconnection between them are shown by a straight line even though the system is three-phase system. That is, whether the system is a single phase or a three-phase system, the components that will be represented easily by this single line diagram. And after drawing the single line diagram, the ratings of each and every components will be represented above the components. Now, let us see the standard symbols for each and every component used in power system. Here, the rotating machine that will be represented by this circle. And this is the representation of a two-winding transformer. And this is the representation of a three-winding power transformer. And this is power circuit breaker. And then this is air circuit breaker. This is the representation of three-phase delta connection, three-phase star connection, and the last one is star connection with neutral grounded. So these are all the symbols that is used to draw the single line diagram. Next, let us see the definition for per unit value. The per unit value of any quantity is defined as the ratio of actual value divided by base value. In power system, all the values, that is the voltages, currents, all those things that will be represented by the per unit value. And here, let us see what is meant by base value. What is the necessity to calculate these base values? Actually, here, all the components or various sections of power system may operate at different voltage and power levels. So, we cannot take the values as it is. So, for analysis purpose, all the voltages, power, current, and impedance of all the components are expressed with reference to a common value that will be termed as base values. So after taking the base values, we can calculate the per unit value for analysis purpose. Now let us see what are all the advantages of per unit system. So normally while designing all the components itself, the manufacturers, they will be generally specify the ratings of each and every component, and any unknown value can be easily assumed if the representation which is in per unit. And the next point is the per unit impedance of a transformer, which is same whether it is respected to primary side or the secondary side. And the per unit calculation, which is very simple comparing to all other methods. And the next point is the values when represented in per unit, which lies in a narrow range. So if any error occur in the calculation, it can be easily identified. And the per unit systems are ideal for the computerized analysis and the simulation of complex power systems. For a three-phase transformer, per unit calculation is same for both star and delta connected networks. So these are all the advantages of per unit system. And in this per unit analysis, we have two formulas to calculate Z per unit. So if all the values are given in per unit, then the formula to calculate new per unit, that is equal to Z per unit old into KVB old by KVB new the whole square into MVAB new divided by MVAB old. And the second formula to calculate Z per unit new, that is equal to Z into Z, that is the actual value divided by base value. Then, if the values are given in terms of ohm, we have a different formula. that is Z per unit mu, that is equal to Z actual divided by base value. Z actual divided by Z base. And here the Z base value, that is equal to the formula to calculate ZB, that is equal to KVB the whole square divided by MVAB. Now, this formula can be rewritten as Z per unit mu, that is equal to Z actual into MVAB mu divided by KVB mu the whole square. So, there are two formulas are used here to calculate Z per unit mu. One is nothing but Z per unit mu is equal to Z per unit old into KVB old by mu the whole square into MVAB mu divided by MVAB old. And the second formula, if all the data for all the components are given in terms of ohms, then we can use this formula to calculate Z per unit mu. And here we can see the equivalent circuit of various components in power system. First one is synchronous generator. So this is the equivalent circuit of the synchronous generator. The equivalent circuit of the synchronous generator, which can be drawn with the source and its reactance value. Similarly, the synchronous motor, that is nothing but its EMF value as well as its corresponding reactance, and transformer or transmission line, which is represented by its reactance value. The only difference between the generator and motor is nothing but the direction of current flow. Here for the generator, the current flow is from the generator towards the load, and for motor, it is from the supply towards the motor. This is the difference between the generator and motor. Now let us see the procedure to draw the impedance diagram. So why we need this impedance diagram? Because this impedance diagram, which is mainly used in load flow analysis, that is for in load flow analysis for calculation purpose, we require this impedance diagram. And to draw the impedance diagram, we require some approximations. So let us see the approximations that made in this impedance diagram. So the first point is nothing but the neutral reactance, which is connected between the generator neutral and the ground, that is neglected. So here this is a star connected neutral um, um, and which is connected by means of a reactance. So if the connection is like this, then the neutral reactance between the neutral as well as the ground can be neglected. Similarly, the shunt branches of the equivalent circuit of the transformers are neglected. So all of you know the transformer, which consists of a primary and the secondary circuit. In the primary circuit, we have an magnetizing circuit, and this magnetizing circuit can be neglected while drawing the impedance diagram. So these are all the main approximations that is made while drawing the impedance diagram. And for this equivalent circuit or single line diagram, here the impedance diagram is drawn. So here in this single line equivalent circuit, which consists of a generator and a motor, then two transformers T1, T2 and a transmission line. This is a transmission line. For this single line diagram, we need to draw the impedance diagram. So the first component is nothing but a generator. So for this generator, the equivalent circuit is nothing but generator, resistance, and its EMF value. So EG, R, as well as its reactance. And the second component is nothing but transformer T1. For transformer T1, actually, we have a resistance as well as a reactance. And then the transmission line, which is represented by a pi equivalent circuit, which will consist of again resistance, reactance, as well as its corresponding capacitances. And then the next component is nothing but a transmission line. So this transmission line again, which consists of a reactance and the resistance value. And then finally, we have a motor, uh, transformer T2, and then a motor. For a motor circuit, actually, which will have a reactance value as well as resistance. So this is nothing but an impedance diagram for this single phase, single line circuit. Similarly, the second one is reactance diagram. So in this reactance diagram, again, we need to make some approximations. So the first approximation is the neutral reactance, which is connected between the generator ground and the neutral, can be neglected. The second point is shunt branches of the equivalent circuit of the transformers can be neglected. And the third point is all the resistances of the entire components can be neglected. And the fourth point is all static loads are neglected. And the last point is the capacitance connected in the transmission lines can be neglected. So these are all the approximations that made in this reactance diagram. In the impedance diagram, we have seen that only the neutral reactance connected between the generated neutral and the ground is neglected, and the shunt branches of the equivalent circuit of the transformers are neglected. In addition to those 2 points here, 3 more points are added. The resistances of all the components will be neglected, all the static loads are neglected, and then capacitance of the transmission lines are neglected. And this reactance diagram, which is mainly used in fault calculations or short circuit analysis. And here, this is the reactance diagram. We can consider the same single line diagram. For the same single line diagram, here the reactance diagram has been drawn. First component is the generator. So what is the procedure to draw this reactance diagram? First step, that is we need to neglect all the resistances. So for all the components, all the resistances has been neglected. So the generator, which is represented by its source and its reactance value. And similarly for a transformer, the resistance is neglected and the transformer which will have only the reactance value. Similarly, the transmission line, which also have only the reactance and there is no resistance, as well as there is no capacitances in the circuit, and the static loads in both the circuits, that is neglected. Okay. And then for a transmission line, we have a capacitance in the previous impedance diagram. So that capacitance, that also have been neglected. And similarly for a transformer, again here, uh, the resistance is neglected. And for motor, again, the resistances are neglected. So this is the reactance diagram for the single line circuit. Now, uh, mm, let us discuss about the procedure to form impedance and reactance diagram from the single line diagram. So the first step is we need to select the base MVA and base KVB. Okay, so how to select base MVAB? Um, Suppose in the problem, if this MVAB which is not specified, then we need to take the highest value, highest MVAB value given in the components. So whatever maybe, whether it is a generator or transformer or transmission line, which MVA that is higher value, that will be chosen as base MVA. This is the first point. And the second step is nothing but we need to choose KVB. So how to choose KVB? Suppose if the KVB value which is not specified in the problem, then we need to choose the highest, the voltage of the highest section of the single line diagram. Normally the highest section in the single line diagram is nothing but the transmission line. Suppose if the KVB value, that is the base KV value which is not specified in the problem, then we need to take the transmission line voltage as the base value. And remaining all the sections, we need to calculate KVB new value. So in order to find out new KVB, we have two formulas. If it is KVB on low tension side of the transformer, then the formula to calculate KVB for the particular section, that is equal to KVB on HT side of transformer into LT voltage rating divided by HT voltage rating. Similarly, if it is referred to high tension side, then the formula which is used to calculate KVB for that section is KVB on LT side of the transformer into HT voltage rating divided by LT voltage rating. See here this left hand side is HT. So in the right hand side it is LT into HT divided by LT voltage rating. So by using these two formulas, we can able to calculate the KVB new for the remaining sections. Then after choosing MVAB and KVB, then the next step is to calculate the per unit reactances or the impedance value. As I told earlier, if all the values are given in per unit, then we can use this formula to calculate a new per unit value of impedance. That is Z per unit mu, that is equal to Z per unit old into KVB old by KVB new the whole square into MVAB new divided by MVAB old. So this is in the case when for all the components are specified by per unit values. If all the reactances are given in terms of ohms, then we can use this formula to calculate new impedance value, that is Z actual divided by Z base. Z base is equal to KVB the whole square divided by MVAB new. So by using these two formulas, we can calculate the value of Z per unit new. Then after calculating Z per unit new for all the components, finally we can draw the impedance and the reactance diagram. So this is the procedure to draw the impedance and reactance diagram. Thank you.